Hello. In part 1, we looked at transforms, parent and reparent constraints, and in this video we're going to look at the rest of the KineFX constraints. Look at constraint, as the name implies, makes the object look at specific direction. For that we need a target position and the up vector. So let's start by taking this transforms geometry node and rename it look at constraint. And we want this object to look at specific target. So first, I'm going to just disable this connection and just move the target somewhere. So we want this object to look towards this target position. And now let's create a look at constraint, which is look at KineFX node. And from parameter tells from which position we are looking at. So in this case, we are looking from this object position. And we're looking towards this target position. So we connect the work transform of this target point into two parameter, and the output of this look at constraint we connect to the set point transform, which will set the transformation for the object point. Now if we move the target around, we see that the object is rotating towards this point but is oriented incorrectly. And this is because we must set correctly the look at axis, which in this case should be Z, and up axis, which should be Y. Now the look at axis tells which axis of the object joint we look towards the target position. And if we go up here and let's just display, this is the object joint. We want this is the Z-axis, we want the Z-axis to aim towards the target position. That's why the look at axis is Z. And the up axis basically tells which axis will be used to determine how the object will be rotated or rolled around that axis that is looking towards the target position. Now notice that the up vector can be also provided as a separate transform. So you can have a separate point as the up vector, and we're going to just duplicate this network and just rename this to be the up, and maybe create a different type of control for the up vector. And this will be recompose up, and we're going to connect it to the third input. I'll just move it up here and use the green control. So now if we go back to the constraints and get point transform for the up and from the third input, and we connect the transform for the up parameter of the look at constraints. We can now see that, let's just hide this. So if we move around the up point, which is used for the up vector, we are now rolling around the look at axis. And I see that the up control is not displayed correctly. And this is because I forgot to set the group name correctly in the attach control geometry, and now the up control is displayed as green control as it should be, and the red one as the target position. And this is the basic look at constraint. We can also apply a look at constraint with blend and offset. And all we need to use is a look at constraint which is the same as look at constraint we use, which has the added blend and offset options. And again, I'm going to just copy this geometry node, rename this look at blend and offset constraint, and go into the constraints network. And if we add the look at constraint, right now we have used this one, look at KineFX. And if we create this one, look at constraint, we see we have additional update and clear offset and blend options. And if we now reconnect everything, so the X form goes for the object point, target point goes to look at, and the up point goes into the look up parameter. And we will also promote the blend parameter. Now, if you just test our constraint, we see it works the same way. But now we have the blend option, which blends from the default position to constraint position. And if we go back to constraints and update the offset, so first we have to set the blend value to 1 and update the offset, we see that now if we move this constraint, we are moving from this offset position. And when we want to reset the offset, we just click on the clear offset, and there is no offset for the constraint. And this is how we can have a look at constraint with blend option and offset. Now it's time to look at curve or path constraints. We can attach the object to follow path and look at a specific direction, for instance. Let's start by duplicating this transforms geometry node, name it path constraint. And we will not need this control setup, so we can just delete this whole part. But we will need to create a curve object on which this object will be moving. Something like this. And we can create an URBS curve for this. And we let Rig Doctor create the necessary name attribute. And we'll connect this one into the second input of the constraint. And now if you go into the constraint network, we don't need this target point, but we will need to create the transform from path. And since our curve is connected to the second input, we'll use the file as the second input. The primitive number will tell which primitive to use. In this case, we only have one curve, so it's only one primitive, so the primitive number will be 0. The curve position will tell where on path our object should be. So first let's connect the out X form into the X form of the object transform output. So if we, for instance, let's just display the curve, and first let's just promote this curve position parameter. For some reason, the curve position is not updating properly. Let's just... Okay. So it seems it only needed to refresh the constraint network. So the curve position is now telling where on this path the object is. And since we want the object to look ahead, we can change the get look at from to look along the curve. And we can just have to make a small offset value. So that far ahead of the curve, this object will be looking. So the greater the number, further along the curve, the object will be looking. So now the object is following along the curve nicely. And we can also change the up vector to get it to either use the attribute or the vector we provide here. Okay, so let's expand a bit on our path constraint. So let's set up a network where we wish to look at a specific target while the object is moving along the path. Let's start by first copying the path constraint object and rename path constraint look at target. And we will also require a target point, and why don't we just copy it, this type of setup, from the transforms object. I'll just paste it here, connect it to the third input of the constraints, and let's move the target point into which we want the object to look at somewhere here. Now let's go into the constraints network, and what we want to do is, instead of looking along the curve, we will provide a vector. And this vector we will calculate from the target position and the object position. And if we subtract these two positions, we get a directional vector that we can use as a look at vector. So first we will need the position of the target. Which is connected to the third input. And we need to extract the transform of the target point. So we get a separate translation, rotation, scale, and shear, but we only need the translation for the position. And to get the position of this object on this path, we will use another transform from path and use the same curve position parameter, and then use the extract transform the same way as we did for the target. So now we have the positions in space for both the object and the target, and if we subtract these two positions, we get a directional vector that we can use in this transform from path as a look at vector. So now we see that the object is always looking towards the target position. Okay, so let's create another example for our path constraint. Let's add the option to roll the object along the path. To do that, we will need to get the tangent and up vector from the path and use that to calculate the roll along the path. So we'll start with the first path constraint and we'll just rename it to path constraint with roll. Let's go into the network. And first we will need to have the tangent and up vector for the curve, and we can just use the orient along curve sub, but this one requires the polygon curve, so the NURBS curve has to be converted. In this case, we'll just use the resample. And let's see how dense we want to have this. So this is a bit too dense, and maybe a length 0.2 will be enough. And now, if we look at the orientation along curve, we see that the n vector is basically our tangent vector. So I'm going to just rename the n to tangent. So this is our tangent vector, and this is our up vector for the curve. Now we can go into the constraints network, and all we need is now get this information into this network, and we can use the primitive attribute WAP, and this one will sample our curve at specific position, and for this curve we need to only sample at specific u position, which is actually the curve position, and we will be sampling the up and tangent, so this one will be up. And to define geometry file, we want to sample the second input into which this curve is connected. So we can use the geometry WAP global parameters and connect the input 2 into the file. And now we have a value of up vector on the curve at curve pos position. Now if we duplicate this one and just rename it to tangent, and the attribute that we are sampling is the tangent, now we have also the tangent attribute. Now we want to define how much we roll around the tangent axis, so we need to add a parameter, and this will be the roll parameter, which will be a float, and the range is minus 360 to 360 degrees. And to rotate the object along the tangent, we will use the rotate WAP, and this one will rotate the given matrix around the given axis, which is our tangent. So we want to create an identity matrix, and we can do that by just creating the constant and use the 9 floats 3 by 3 matrix, and we will connect the output of this matrix to the math parameter. The roll should be the angle or how much we are rotating, but this one requires radians, and here we want to have in degrees, so we're going to just use degrees to radians. And the axis around which we are rotating is the tangent on the curve. And now we can multiply our new matrix that we get from this rotate with the curve up vector, and this should give us a new up vector, which will be used as a roll in this case. So if we multiply the up vector with the output of rotate, we get a new vector that can be used as a lookup vector. So now let's see how this works. So now we have a roll around the tangent of the curve. So we can manually animate this parameter to define how the object is angled along the path. And this is how we can use constraints with other matrix operations and nodes to get, in this case, a custom role transformation for our object. Now let's look at surface type of constraints, and we can constrain the joints to a specific primitive or nearest point on surface, for instance. And let's first look how to constrain to a specific primitive. And let's start with a path constraint setup and rename it primitive on surface. And we don't need the curve part of the setup. And we can delete the transform from path from the constraint network. And now we need to create this geometry that we will use to constrain the point to. So let's use the template head. And let's just scale it up a bit. Something like this should do. Now let's connect the test geometry to the second input. And notice we get an error. And this is because the constraint rig attribute VOB is computing the transforms also for this geometry. So under the rig tab, we have to disable the compute transfer for the second input. We only need to compute the transforms for the first input, which is the object point. Now let's go into the constraints network. And here we're going to use the transform from surface constraint. Now the output transform goes into the set point transform. And right now we can just change the primitive number, but first we have to set for which input are we calculating. And since the geometry is connected to the second input, we have to set the file to the second input. And now when we change the primitive number, we are constraining to that specific primitive. And we can promote this parameter. And notice that nothing is now happening. And this is because primnum is a reserved global variable that cannot be used as a parameter. But if we change the primnum parameter to anything else, for instance, if we change it to pinum, it should work just fine. And we can make a greater range for the choice of primnums, for instance, 0 to 500, and now it should work just fine. So we just decide on which primnum we want the object to be constrained to, and that is the primitive on surface constraint. We can also orient this object to use this surface normal. All we have to do is add the normal to primitives for the surface and the constraints network. Instead of get look at from vector, for instance, we can use the attribute. And now if we add the normal, we can now see that it is always looking in the direction of the surface normal. Now we have constrained the object to a specific primitive. And now let's create another setup in which we will constrain the object to the closest primitive on geometry. Now let's start with the primitive on surface setup and rename it closest primitive on surface. Let's go into the constraints network. We will not be using the primnum parameter as we will calculate which primitive is closest to the object position. So for that we will need the extract transform and connect the object transform to extract xform parameter. And now we have the position in space. Now we will need to calculate which primitive is the closest to this position. And for that, we can use the XYZ distance and connect the translate to the pos parameter of XYZ distance. And we also need to define the geometry file, which is our surface. And we can use the geometry, global parameters, and use the second input to which the surface is connected to as the input. And now we have the primitive number. And the primitive number we can now connect to the transform from surface. And now if we add the rig pose to move our object around, we see that our object is now constrained to the closest primitive on this surface. Now, just in case you want to animate our closest point on surface constraint, we can just use the blend transform sub and use the blend transform, and the first transform will be the point transform, and the second one transform from surface, and the output of this blend transform it's going to the set point transform for the object point, and we can promote the bias parameter. So now we can animate the constraint from the object position to the closest point on surface. And this is how to set up the closest primitive on surface constraint. So this was an overview of KineFX basic constraint setups. I hope you found this video useful, and see you next time.